Yeah, good morning to all, and welcome back to Basic Circuit Theory. And it's me, Paul Turai. I hope so you can remember me since after a long time. Okay, and this is lecture number 30, and till lecture number 29. Okay, from 27 to 29, we have been discussing resonance. So, I started with the resonance. Anyone? What is resonance? What is the definition for resonance? According to my definition, what is resonance? Anyone? What is resonance? Anyone?
So when total applied voltage and current are in phase, even though inductor and capacitor are
Hmm,
present,
very good,
uh,
very good. Yeah, thank you. So, in simple words, okay, the current is in phase with the applied voltage, right? Resonance occurs, resonance occurs when the current, okay, of the circuit is in phase with the applied voltage. And as we discussed earlier, we are having two type of resonance. One is called series resonance, parallel resonance, and we have been discussing series resonance. Series resonance, so as the name indicates, how will you sketch the circuit diagram for series resonance? You will connect one R, one L, and C, okay, in series, and you will apply some voltage, and this is my applied voltage. Okay, take some Vs, source voltage, R, L, C. So here, what is the condition for resonance? When XL equals XC. Okay, so this is the condition for resonance, that you know why. Now, how will you find the resonance frequency? In order to find that, you know what is XL equal to L omega, Xc equal to 1 by C omega. Take the magnitude. I'm looking for omega. Okay, so omega squared equal to 1 by LC. And what do you mean by resonance frequency? The frequency at which resonance occurs. So here this omega becomes omega R. Okay, so this is in terms of radian per second. Since omega equal to 2 pi f, so this is 2 pi f r equals 1 by LC. Therefore, resonance frequency equal to 1 divided by 2 pi. Actually, this is square root of LC, right? Yeah. So 1 divided by 2 by square root of LC. Heads, right? So this formula, So these two formulas are important. Resonance frequency in terms of radian per second, and the resonance frequency in terms of hertz. Okay. So we started with the series resonance. First we derived, or we found the resonance frequency in terms of radian per second and hertz. After that, what we discussed, that variation of three things. First one is impedance, next one is current, and the final one is voltage with respect to frequency, right? So variation of Z, I, and V. This what is the variation of first impedance in terms of frequency in terms of hertz? This is my impedance. Okay, at resonance, you will get a curve like this, right? How we got this curve, that oh, I don't want to repeat that. At resonance frequency, this impedance is minimum. It is given by almost R, right? Okay. What about this range? When the frequency is less than resonance frequency, who is dominating? And what about this range? Anyone? This is the frequency, okay, which is less than resonant frequency. This is the frequency which is greater than resonant frequency. Yeah. In region 1, who is dominating? Region 2, who is dominating? Anyone?
Sir, region 1 capacitance and
So
region
here
2.
XC is greater than XL, that you know why. So here XL will be greater than XC. Now at resonance, what is your impedance? At resonance, who is dominating? At resonance, Z equal to R. Okay, resistive in nature. Okay, this is the variation of impedance. Now variation of current, variation of current. Since as per Ohm's law, I equal to V by R, right? So both this R as well as this I, okay, resistance, nothing but impedance and the current, both are inversely proportional to each other. So if we will sketch the curve, okay, for current I in terms of ampere, right? This is in terms of ohms. So now the curve எப்படி இருக்கும், that at resonance you will get the maximum current, and this current is given by applied voltage divided by R. Okay, so this then we discussed the variation of voltage, right? Variation of voltage. Since series circuit, we connected R, L, C in series. So what is the voltage drop across R? What is the voltage drop across L? And what is the voltage drop across? So here also it is frequency, but this time it is volt, right? So I discussed earlier, applied voltage Vs. This is my resonant frequency. Okay, now this is my voltage across R. Okay, so when you will get maximum voltage drop across capacitor? Any idea? Maximum voltage drop across capacitor occurs before FR or after FR? Anyone?
Before.
Before, right? You know the reason why. Then after. Okay, so take this is my voltage across capacitor, and this is voltage across inductor, right? And this frequency we termed it as f of L, and this frequency we, sorry, this is FC, right? F of C, and this is f of L. What is the formula to calculate f of C? It is resonance frequencies multiplied by a factor 1 minus R squared C divided by 12. Then what is FL? The same resonance frequency, this time divided by the same factor, right? 1 minus R squared C divided by 12. Okay. So this is about the variation of voltage. Then what we discussed? Anyone? First is series resonance, then variation. What's the third topic? We started with bandwidth. Okay. And do you know how to calculate bandwidth? And what is the formula for bandwidth? If we have direct bandwidth is given by R divided by 2 pi L in terms of hertz. In terms of radian per second, bandwidth is actually F2 minus F1 or FH minus FL. Right. In terms of radian per second, it is R by L. Okay, so this is omega 2 minus omega 1, or otherwise omega H minus omega L, that we derived. After that, what is the relation between this omega L, omega H, and omega R? That we derived. So omega R squared, we have got omega L times omega H. Okay, so this is about the bandwidth. Okay, we derived the bandwidth from this formula. Then we discussed variation of series resonance circuit. And guys, I'm audible.
Yes, sir.
Energy, like I interrupt, right?
Yes, sir.
Network problem, I think so. So screen is presented or not? No.
No, sir.
Okay, let me present it. So where we are? தனியா என்ன பேசிட்டு இருந்தேன்னு தெரியலையே.
As a
எது வரைக்கும்
bandwidth
okay, so bandwidth.
ending.
Okay, so bandwidth, this is our bandwidth, right? So bandwidth in terms of hertz, it is R divided by 2 pi L. In terms of radian percent, it is R by L, right? And we started with the quality factor. Guys, are you with me? Am I audible?
Yes, sir.
Okay, so quality factor, what is quality factor? Anyone? The ratio between the voltage across inductor to the applied voltage, or otherwise the voltage across capacitor to the applied voltage. Now, what is the formula to calculate the voltage across inductor? As per Ohm's law, V equal to I times R. So here I times, what is R? XL, right? So I times, here it is XL divided by, what is the voltage drop? Okay. What is the applied voltage? At resonance, it is I times R, right? Applied voltage or the voltage drop across, actually this is resistance, right? In this way also you can define the voltage drop across resistor at resonance. That's important. At resonance, in this way also you can define. Okay, so since series circuit both I are same, so this quality factor is XL by R, where XL equal to L omega by R. This formula is important, or otherwise if you will use this formula, okay, so Q equals this time VC by applied voltage. Applied voltage at resonance. At resonance, all the voltage drop must all the voltage, okay, must drop across resistor. So it is I times R. So here it is I times XC, right? So here also series circuit. So IA will be cancelled. So this time XC by R, where XC equal to 1 by C omega R. At resonance frequency, so omega becomes omega R. That's very important. So these are all the formulas for quality factor. Then we derived one more interesting relation. Okay, the relation between quality factor and bandwidth. It's very important. Okay, relation between quality factor Q and bandwidth. What was the relation? That was my last topic. Okay, so what is quality factor from this? Okay, this quality factor Q equals L omega R divided by R. Okay, it becomes, what is this? Omega R divided by R by L. Okay, what is this R by L? This is omega R divided by, this is bandwidth, but in terms of omega, radian per second. Okay, in terms of radian per second. This is one way, or otherwise, what is my quality factor? Q equal to, L omega R divided by R in terms of F. So where L omega R equal to 2 pi FR, okay, divided by R. So it becomes FR divided by R divided by 2 pi L. And what is this? R divided by 2 pi L. R divided by 2 pi L. This is my bandwidth in terms of F, right? So it becomes FR divided by bandwidth. This time in terms of F, or otherwise in terms of Hertz, right? Yeah. So quality factor, the conclusion quality factor, okay, is inversely proportional to bandwidth. If it is in terms of radian per second, then here it is omega r. In terms of hertz, then it is FR, right? So these we discussed in the last class. Any doubt till now? Any doubt till now?
No, sir.
Okay, so the final topic, okay, in series resonance, as I have given in my syllabus, or it is selectivity. Selectivity. As we discussed earlier, you know the range for FM, right? It is 88 megahertz to 108 megahertz. Okay, suppose I am asking you to search for radio Mirchi. What you will do? I'm asking you to search, or I'm asking you to fix the FM station at radio Mirchi. What you will do? You know the frequency range for radio Mirchi, it is 98.3 megahertz. So immediately, from 88, you will start from 88 because it starts from 88. Then you will fix it at 98.3. I'm asking you some other station. Okay, let me assume Kodaikanal FM. Okay, assume you don't know the range. At the time, what you will do? I'm asking you to fix it at Kodaikanal FM. It is there, ma. Anyone? Do you know the frequency for Kodaikanal FM? Actually, it is a government. The Kodaikanal FM government order actually, government undertaking. Or like Sun, Sun TV. What is that? Suryan FM, Radio Mirchi, இதெல்லாம் private. Anyone have you heard Kodaikanal FM?
Sir, 100.5, sir.
Kodaikanal I'm speaking. That is a rainbow. Rainbow da 100.5. Kodaikanal it is I think so 100.5 correct I think so. Because 106.4 that is allowed.
Sir, Madurai side la sir varum.
100.5 தான் சார்.
100.5 தான் சார்.
100.5. 100.5. You're correct. 100.5 megahertz. Okay. Just assume you don't know this frequency. So what you will do? You will start from 88. Okay. So between 88 to 108. Okay. You will search for that Kodaikanal FM. Okay. And you will fix it. Okay. Since the range is very limited, right? 88 to 108. What is the bandwidth? What is the bandwidth for this FM? Anyone? Bandwidth.
Sir, 20 megahertz, sir.
20 megahertz. So the range is limited, so it is easy to select the particular station. Suppose, let me give one more example. Suppose the range is some 8 megahertz to 108 megahertz. This time I am asking you the same task. This time also you want to fix Kodaikanal FM, but you don't know that frequency range. This time what you will do? You want to start from 8 megahertz. This time what's the bandwidth? The bandwidth is 100 megahertz almost.
100 megahertz.
So it is very high. So which one is easy? The first one or second one? For to select a particular
first one, sir.
First one. So what is the relation between selectivity? Selectivity in the sense you are selecting a station, right? There is about selectivity. What is the relation between selectivity and bandwidth? Any idea?
Inversely proportional.
So both are inversely proportional. Okay, so bandwidth. Here also it is either FR. So this time bandwidth in terms of hertz or omega R. So this time bandwidth in terms of radian per second. So what is this actually? Nothing but quality factor. Okay, so the other name for quality factor is nothing but selectivity. Both are same. Okay. Nothing new. Okay, so selectivity is nothing but quality factor. In another way, we can define quality factor in the name of selectivity. Okay, so the conclusion is very important. Selectivity and bandwidth both are inversely proportional to each other. Okay, so this is about series resonance. Now coming to parallel resonance. What we discussed in series resonance, the same thing we want to discuss in parallel resonance. So here also I want to start with the concept of parallel resonance first. Okay, when parallel resonance occurs, what is the resonance frequency? Okay, then we want to discuss what is the variation of this guy, impedance, current and voltage with respect to frequency. Then we want to discuss three interesting parameters, the same parameter bandwidth, okay, quality factor, Q, simple words, and finally here also selectivity. Once if series resonance is understood, then it is easy to study parallel resonance. So now what is the concept of parallel resonance, right? So let me put the heading parallel resonance. This time, how will you sketch the circuit diagram for parallel resonance? Anyone? Series resonance is very simple, right? There is only one way. You will take one R, one L, and C. Okay, you will connect this in series, and you will apply some voltage. That's it. Okay, this is your series resonance. Coming to parallel resonance, so first you will take one R. This time you will connect R, L, C in parallel, right? Then one L, then one C. And here you will apply the voltage, source voltage, R, L, C. So this is parallel resonance. Okay, but here the beauty, not only this circuit, okay, you may have different ways, okay, are there to connect R, L, and C in parallel. So what are the remaining ways? See, sometimes this inductor, right, it may have some internal resistance, okay, in series with this inductor, you may have some resistance. So at that time, you want to connect the C as it is. Since here I am having R, so no need to connect separate R. So straight away give this applied voltage. Circuit 1, this is circuit 2. This is also parallel resonance. Or otherwise, not only this inductor, sometimes this capacitor also it may have its own internal, right? Like us. We people also having your own internal, right? Own internal resistance, right? So this is take this time R, this is R. Okay, since two R are there, so take this is the R's of L. Since this is my L, so in series with RL, this is my C, so take this is R's. So here now apply circuit 3. Any other circuit? Yeah, sometime the capacitor alone it may have it own internal resistance. This is L, so this time this I can keep it as R alone since only one R. So this is also possible. Circuit 4. Okay, we want to find the resonance frequency for each circuit. Okay, in communication, we will use circuit 1, 2, and 3 mostly. Why? That I will explain later if time permits, because I want to deal with the communication point of view. Circuit number 4, most probably we won't use. So I want to take the first 3 circuits, and my aim is I want to find the resonance frequency. Okay. You know what is the concept of resonance? The same. Okay. The applied current, applied voltage and the circuit current are in phase, as you told. Nothing changed, nothing new. But this time, since we are dealing with the parallel circuit, so 3, okay, the 4th one is not required for you people. Okay. So we want to find the resonant frequency for these three circuits. What is the resonant frequency for parallel resonance? Anyone? Sorry, series resonance. Resonant frequency for series resonance. Anyone? In terms of hertz. 1 divided by 2 pi square root of LC.
LC.
Okay. So first take the first circuit. Let me take the first circuit and to derive resonance frequency. First circuit. Okay. How will you find the resonant frequency? Let me explain the flow. Just listen. The flow is, in order to calculate resonant frequency for any circuit, it may be circuit 1, 2 or 3, the flow is same. So let me explain the flow first. It's very simple. First find impedance. Find impedance, right? Z, total impedance. What is the condition for resonance? You know, impedance Z equal to some real part, okay, plus some imaginary part. It may be XL or XC, okay. In general, take some X, okay. It may be XL or XC, combination of XL and XC. When resonance occurs, at resonance, you will get only real part, right? At resonance, you will get only real part. So what will happen to imaginary part? Imaginary part becomes 0. So you want to find the impedance, okay, and make this imaginary part equals 0. Okay, so this is the flow. You want to calculate impedance and make the real, you know, when you are calculating impedance, you will get real and imaginary part since you are playing with RLC. So make the imaginary part as 0, then you can. So this is the flow. Okay, so find impedance and put imaginary part, okay, equals 0, then you can easily find. Let me find, okay, for the first circuit RLC. What is my impedance here? What is my impedance here? Anyone? For the first circuit, impedance, or it is connected in parallel with, what is the impedance offered by inductor XL in parallel with XC, right? So it is R parallel with, what is XL? It is J times L omega parallel with, what is XC? It is 1 by J times.
1 by JC omega.
Okay. What is the formula? You know, if R1 and R2 are connected in parallel, how will you write? They take this by R equivalent. So the formula is, you know, 1 by R equivalent is 1 by R1 plus 1 by R2. This formula you know, right, from our unit 1. So similarly here, 1 by Z equals 1 by R plus 1 by JL omega plus 1 by 1 divided by JC omega. What is 1 by Z? It is nothing but Y. Okay. Admittance. This is impedance. The reciprocal of impedance is admittance. Okay. So it is 1 by R plus 1 divided by JL omega plus JC omega. Okay. So this is 1 by R. Since my aim is I want to find real and imaginary part. So what is 1 by J? How can you write 1 by J? 1 by J multiply and divide by J. It becomes J divided by J square. So can I write minus J? So this is
Yes, sir.
minus, right? This is minus J divided by L omega plus J C omega. So it becomes 1 by R. Now take J as common. So C omega minus 1 by L omega. This is my admittance, right? Either you can find impedance, but here this is parallel circuit, so you can find impedance or admittance. Okay, since this is admittance, right? So now what do you want to do? What is the name for this imaginary part? Now this imaginary part, okay, since it is my admittance, right? The admittance ஓட imaginary பார்ட்டுக்கு பேரு susceptance. Okay, don't confuse, this is just technical name. My aim is, what you want to do? You want to calculate the real, imaginary part of this admittance, and you want to equate that one to 0. Okay, so now at resonance, what will happen? You will get only resistance, right? So what will happen to this imaginary part? It becomes 0, right? Therefore, at resonance, C, at resonance, omega becomes omega r minus 1 by L omega r equals 0, right? So C omega equal to 1 by L omega. What is this? Looking for, so C omega r, right? So omega r squared equals 1 by LC. Therefore, omega r, once again, same formula, right? What we got for series resonance, the same formula. So omega r equal to 1 by LC square root of LC radian per second. Here omega r equal to 2 pi fr. So 2 pi fr equal to 1 divided by square root of LC. Therefore fr equal to 1 divided by 2 pi square root of LC in terms of hertz, right? So for circuit 1, same formula what we got in series resonance. So now take this. Got the flow? First you want to calculate impedance. So here parallel circuit, so you want to calculate admittance. Find the real and imaginary part. We know at resonance the imaginary part becomes 0, susceptance becomes 0, technically speaking. So making the susceptance equals 0, and we came up with the resonant frequency formula in terms of radian per second as well as hertz. But the beauty, again the same formula. Okay, now take circuit 2. So this time this R, it may, okay, in series with this L, so it becomes R. Now this is my C. And here I want to apply my. Now for this circuit, we want to derive the resonant frequency. Can you derive by yourself? Again, the same flow. If you will derive, we will end up with resonant frequency FR. The same formula 1 divided by 2 pi. Okay, square root of 1 by LC. What is this R? So it becomes minus this R squared, this L squared. So it is very easy to remember the formula. I repeat. Okay. The resonance frequency formula FR, 1 divided by 2 pi square root of LC, right? So square root of LC, but this time since I'm having R and L, so it becomes R by L the whole square, or otherwise R square divided by L square. Okay. So let me derive this. So here also, I want to calculate this impedance. Okay. Impedance Z equal to, this time, what is this impedance? You are having real and imaginary part. Let me take, this is my Z sub L. Okay, ZL, which is equal to real part is R, since both are connected in series. So R plus J times XL, where XL equal to L omega. Okay, so R plus J times L omega. Here it is XC equal to 1 by J C omega. Okay, so here total impedance Z can be Z equal to ZL parallel with XC, right? Any doubt? Where ZL equal to R plus J times XL parallel with XC, right? So This is my Z. So 1 by Z equal to, you know the formula, 1 divided by R plus J times XL plus 1 over XC, where XC equal to, you know, 1 by JC omega. So it becomes, now what will happen? 1 by Z, this is my admittance. So here I want to calculate real and the imaginary part. So what you will do? You want to take the complex conjugate and multiply divided by the complex conjugate. So R minus J XL multiply and divided by complex conjugate, since I want to calculate real and imaginary part. So now this term becomes, okay, JC omega. So now what will happen here? R plus JXL, okay, R minus JXL, A minus B, okay, into A plus B. The formula is, you know, A squared plus B squared, A squared, okay. What's the formula? A minus B, A plus B into A minus B. What's the formula?
Sir, R square plus XL square, sir.
Thank you, ma. R squared plus XL squared straight away, right? Okay, so this is R minus J times XL plus J times C omega. My aim is I want to find real and imaginary part. So separate this part. So it becomes R plus, what is XL? Can I write this time substitute XL? XL equal to L omega. So it becomes L squared omega squared minus J times XL L omega divided by R squared plus L squared omega squared plus JC omega. Okay, so it becomes, you know, R divided by R squared plus L squared omega squared plus take J as common, it becomes C omega minus L omega divided by, okay, so this is my Y. So what I want to do at resonance, you know, at resonance what will happen? Same flow, susceptance becomes 0. So susceptance, you know, therefore at resonance P omega minus L omega divided by R squared plus L squared omega squared. Since at resonance, the omega becomes omega R equals 0. Okay. So now what will happen? C omega R squared equals C omega R L omega R divided by R squared plus L squared omega R squared. Okay. The omega R get cancelled. So now what will happen? So bring this C, okay, to the right hand side, and R squared plus L squared omega R squared to the left hand side. Since I'm looking for, you know, this guy, L squared omega R squared, it becomes L by C minus R squared. Okay. So what is my omega R squared? It becomes L divided by L squared C minus R squared divided by L squared. So L and L squared become cancelled. So what is this? This is my 1 by LC minus R squared by L squared. This is my omega R squared. So therefore, what is my omega R resonance frequency? Nothing but square root of 1 by LC minus R by L the whole square, otherwise R squared by L squared in terms of radian per second. Or otherwise, you know, omega R equal to 2 pi FR. It becomes 1 by LC minus R squared divided by L squared. Therefore, FR equal to, you know, 1 divided by 2 pi square root of 1 by LC minus R squared by L squared. That's right. So this is the way to derive the resonance frequency for circuit 2. Similarly, for circuit 3, you please derive yourself. Okay, straight away I will write the final formula. In case of any doubt, please refer my material. Circuit 3. Circuit 3, this time I'm having two are right, one in series with inductor, another one in series with capacitor. So since I'm having two R, so let me call this is RL, this is RC, and now apply the voltage. Here, one more interesting concept. Okay, here FR, if we will derive, what is the formula? 1 divided by 2 pi square root of LC, same formula, but this time, okay, if we will derive, then we will end up with or L square minus L by C divided by or C squared minus L by C. This is in terms of X. Okay, please try to derive this and let me know whether this formula is correct or not. Yes, I want to test you. How many of you? Okay, please derive. Okay, it won't take more than 10 minutes. You know the flow. So this time find Z. Here Z equal to take this is ZL. This is ZC. Where ZL equal to RL plus J times XL. This is RC plus J times XC. So ZL parallel with ZC. So therefore this is 1 by Z equal to 1 by ZL plus 1 by ZC. You know what is ZL, you know what is ZC. Simple substitution. Then find the imaginary part. Equate that imaginary part equal to 0. Do the manipulation. And finally you will end up with this formula. Okay. Whether this formula is correct or not, that you want to let me know by tomorrow. Okay. So FR equal to, if we will derive, we will get 1 divided by 2 pi square root of LC, RL squared minus L by C divided by RC squared minus L by C. Here one more interesting observation. If RL equal to RC, if these two are equal, what will happen? If RL equal to RC, what is the resonance frequency? FR equal to 1 divided by 2 pi square root of LC. That's right. So this is the resonance frequency formula for the circuit 1, right? Simple R L P. Okay. So this circuit is almost equal to RLC when if RL equal to RC. Okay. So that's the interesting observation. Let me know whether this formula is correct or not. That is your job. Okay. You want to let me know. Okay, by tomorrow, second hour. So this is about the very first topic. Okay, on resonance frequency, concept of parallel resonance, and the same concept. Resonance definition is same, but this time since three circuits. Okay, so you want to know the resonance frequency formula for each circuit. Okay, they may give any circuit, and your job is you want to calculate the resonance frequency. Okay, so this time full and full MCQ. So huge probability are there. Okay, any circuit may be given, and you want to calculate the resonance frequency. Okay, so by seeing the circuit diagram itself, you want to write the frequency resonance frequency formula. Okay, so that much practice is needed. Three circuit I have given. So without deriving, you want to know how to derive it, but the best practice without deriving, you want to be in a position, okay, to write the final expression. That is the best way. Okay, அது எப்படி வரும் அப்படின்னா அது because of practice. But you want to practice a lot. You want to derive 2 or 3 times, more than even 5 times. Once if you derived more than 5 times, then automatically அந்த என்ன ஆகும்னா அந்த final expression அதுவே மைண்ட்ல வந்து நின்றோம். That is not by hearting. That is the way. Okay, that is called the practice. By practice, okay, you will get. Okay, I hope so. Like me, நான் அந்த 3 சர்க்யூட்டுக்கும் பார்த்தோன்னே எழுதிடுறேன். அது எப்படின்னா நான் அந்த 3 சர்க்யூட் டெரிவேஷன் ஒரு 5 டைம் எழுதி பார்த்துருப்பேன். அதனால ஓகே. அப்புறம் சப்ஜெக்ட் ஒரு 5 டைம் எடுத்துக்கிட்டு இருக்கிறேன். ஸோ தட்ஸ் அ ஃப்ளோ, தட்ஸ் அ ப்ராக்டிஸ். ஓகே, தட்ஸ் பிகாஸ் ஆஃப் you want to be in the position, you want to be in that position. Okay, how you want to practice a lot. Practice makes a man perfect. And everyone says the golden uh, rule: one time writing equals how many time reading, ma? Anyone? Can you fill that as?
10, sir.
Everyone says 10, but according to me it is 100. Okay, so that much power. So எப்பவுமே படிக்க உட்கார்றப்ப what I will do normally, what I do normally, always I will sit with one pen and A4 paper. அந்த செமஸ்டர் இப்படியே ஆன்லைன்லேயே போயிடுச்சு. ஓகே, முடிய போகுது ஆல்மோஸ்ட். 23 பேர் இந்த கிளாஸ்ல. சத்தியமா சொல்றேன், எனக்கு யாருமே தெரியாது. ஓகே, டைம் பெர்மிட்ஸ் நவம்பர் 16க்கு அப்புறம் காலேஜ் வந்தாலும் இல்லை நெக்ஸ்ட் செமஸ்டர் காலேஜ் வந்தாலும் மை கேபின் ஈசியில் கிரவுண்ட் ஃப்ளோரில். ஓகே, லிஃப்ட் இருக்குல்ல, அதுக்கு பக்கத்தில் ஃபேக்கல்ட்டி கேபின் இருக்கும். இட் இஸ் ஈஸி டு ஃபைண்ட் மை கேபின். அதில் எல்லா கேபின்லையும் பார்த்தீங்கன்னா நேம் பிளேட் இருக்கும், எக்ஸப்ட் ஒன் கேபின், அதுதான் என்னோட கேபின். நேம் இல்லாத ஒரு கேபின் இருக்கும். இட்ஸ் மீ. ஓகே, ப்ளீஸ் ஃபீல் ஃப்ரீ டு கம் டு மை கேபின். சப்ஜெக்ட் முடிச்சா கூட. ஓகே, ஐ ஹோப் ஸோ. ஒன்லி 2 more கிளாஸ். இது ஏன் சொல்ல வந்தேன்னா, இங்கே வந்து பார்த்தீங்கன்னா தெரியும் இந்த கேபினில் எவ்வளோ A4 பேப்பர் இருக்கு, எத்தனை டைம் இந்த டெரிவேஷனை எழுதி பார்த்துருப்பேன். ஸோ தெரியல, இந்த மாதிரி நிறைய A4 கிடக்கும். நாட் ஓன்லி சர்க்கியூட் தியரி, எல்லா சப்ஜெக்டும் இந்த மாதிரி நிறைய A4 பேப்பர் தான் கிடக்கும் இந்த கேபினில். ஓகே, ஸோ அதுதான் சொல்ல வந்தேன். ஸோ first concept over, right? Second one, now let me put the heading variation of, இதை மட்டும் முடிச்சிடலாம். Variation of impedance, current and voltage with respect to frequency, this time for parallel resonance circuit. Any idea? You know all the curve for series resonance. Parallel எப்படி இருக்கும்? Just in negation, right? So first we will discuss that variation of impedance. For series resonance இது எப்படி இருக்கும்னா, ஒரு variation of impedance, frequency in terms of hertz, impedance in terms of ohms. At resonance, at resonance frequency you will get minimum resonance. Okay, so you will get a curve like this. இப்போ இங்க எப்படி இருக்கும்? Any idea? At least guess. Frequency, hertz, impedance in terms of ohm. Here at resonance frequency, will you get a minimum impedance or maximum impedance? Any idea? In series resonance circuit, okay, resonance frequency ல minimum impedance இருந்துச்சுன்னா, parallel resonance எப்படி இருக்கும்? Resonance frequency ல you will get a maximum impedance. Okay, so curve எப்படி இருக்கும்? Automatically if you will sketch. Okay, just reverse of this. Can you relate these two? Okay, just negation, just complement, just reverse, right? Okay, here in this range who is dominating? XC is greater than XL. Here XL is greater than XC. Now coming to parallel resonance, in this range, who will dominate? Any guess? And in this range, who will dominate? So here obviously XL is greater than XC, the reverse of series resonance. So here XC is greater than XL, right? So this is the variation of impedance. Coming to variation of admittance, variation of current. Current actually அங்க எப்படி இருந்துச்சு? If I at resonance you will get maximum current, right? So current எப்படி இருக்கும்? இந்த மாதிரி இருக்கும். So here if you will find, you will get minimum current, okay? At resonance. So obviously எப்படி இருக்கும்? இப்போ வரைஞ்சீங்கன்னா இந்த மாதிரி இருக்கும். இல்லையா? So that's it. Just reverse, okay? The current curve also. So this is the variation of jet and current, okay, for parallel resonance. No more explanation, just from series resonance circuit it is easy to explain. Now variation of voltage. Since this is parallel circuit, so voltage is same. So this time voltage எப்படி இருக்கும்? At resonance you will get maximum voltage, frequency in terms of hertz. This is volt. At resonance you will get, at resonance you will get maximum voltage. So curve எப்படி இருக்கும்? Obviously. So this is the variation of voltage, okay, with respect to frequency for parallel resonance, okay. So we come into the second topic, variation of impedance, voltage and current, okay. So final one, bandwidth. It's very simple. What is the bandwidth formula? So this time I don't want to derive this bandwidth. You know how to derive the bandwidth, okay. So for derivation please refer my material, but if you will derive the bandwidth, F2 minus FL. What is the bandwidth formula for series resonance? It is R divided by 2 pi L hertz, right? So it is here, if you will derive, you will get 1 divided by, since here I am playing with L, R, so here you want to play with R and C, okay, for parallel resonance. So if you will derive, you will get 1 divided by 2 pi RC hertz, or otherwise omega 2 minus omega L in terms of radian per second. So you want to multiply it by 2 pi, so it becomes 1 divided by RC. So this is the bandwidth formula for which one? Parallel resonance, okay. Just remember this formula, R divided by 2 pi L. So here it is 1 divided by 2 pi RC hertz, and bandwidth 1 divided, in terms of radian per second, 1 by RC. And after that, quality factor, the final what is the quality factor definition for series circuit? It is voltage across inductor to applied voltage, but this time for parallel circuit everything is ulta, right? So here also will be reversed. So it is this time Vs by VL. So Vs IR, Vs I times L omega, so IA cancel, so R by L omega. Whereas in series resonance circuit, L omega by R, can you remember that? Take the reciprocal, that will give you R by L omega. Or otherwise in terms of voltage across capacitor, again 1 divided by C omega R. Now take the reciprocal, so it becomes C omega R. So conclusion, quality factor என்ன ஆகும்? அங்க வந்துட்டு voltage across inductor to applied voltage, here applied voltage to voltage across inductor, or applied voltage to voltage across capacitor. Okay, just to take the reciprocal. And the selectivity also same formula. Okay, so this is about parallel resonance. Okay, so hope so this much is enough, okay, for you people, series and parallel resonance. I have given all the formula with a clear explanation. I hope so. So derivation, the bandwidth derivation, please refer my material. Okay, that's same derivation, same flow, like in series resonance. அங்க என்ன பண்ணோமோ அதே flow தான் for parallel.
சார்
Okay,
செலக்டிவிட்டியும் ரெசனன்ட் ஃப்ரீக்வன்சி பை பேண்ட்வித் தான் சார், அதுவும் இன்வர்ஸ் ஆகுமா சார்?
just think. Selectivity அப்படிங்கிறது general. Okay, that is not related to series or parallel resonance. Suppose as per your point, okay, what you are expecting. So what is the selectivity for selectivity? It is in terms of frequency. In terms of hertz, it is FR divided by bandwidth, right? So bandwidth, it is F2 minus FL. Okay. Vignesh, here what you are thinking? This for series. For parallel?
Same.
Same, yeah, very good. Because this is general concept. Okay, you cannot get bandwidth and selectivity are directly proportional to each other, right? Because that explanation will be wrong, right? What I have given, so you will validate that. It becomes invalid. Okay, so actually it is wrong. Okay, so selectivity point of view both are same. Okay, but quality factor, why in series circuit you are applying some voltage, the voltage is dropped. So at that time you can go with this formula VL by Vs. Okay, therefore what is my VL? It is applied voltage into Q times Vs. But whereas in parallel circuit, will it be valid? In parallel, you are applying some voltage Vs. Okay, you are applying some voltage Vs. What is the voltage drop across inductor? What is the voltage drop across capacitor? In parallel, same, right? Actually VL equals Vs, right? So at that time it is not possible to write VL equal to Q times Vs. That's what I have taken the reciprocal for quality factor alone. Okay.
Okay, sir.
So this is the definition for quality factor, and the formula, the formula, it is R by L omega and C omega R. Okay. Whereas here it is L omega by R and 1 by C omega R in series resonance. Okay, just to compare series and parallel resonance when you will be studying, then it becomes easy. Series resonance thoroughly. That's what I took this much time. Okay, ஸ்டார்ட் பண்ணப்போ 20 minutes ஃபுல்லாக நான் என்ன தான் பேசிட்டு இருந்தேன், சீரியஸ் தான் பேசிட்டு இருந்தேன். ஏன் அவ்வளோ நேரம் எடுத்துக்கிட்டேன்? Because if I took this much time, then only I can complete the remaining parallel resonance, okay, in a simple way. So you also please study series resonance, okay, thoroughly, then come to parallel, just update negation now, okay, reverse ulta, then you will get all these except this resonance frequency formula. அதில் சர்க்கியூட் 2-3ல மட்டும் சேஞ்ச் ஆகும், பட் அதுலேயுமே relation கொண்டு வரலாம். Okay, that if RL equal to RC, this relation. Okay, and please verify this formula is correct or not. Okay, you want to let me know by tomorrow. That's an assignment for you people, just a simple assignment. Okay, so this is about resonance. Okay, regarding problem, I planned, okay, to give one assignment for you people for internal 3. So based on this formula, simple substitution, if you know all the formulas I have given, just simple substitution. Okay, so that type of problem may be asked for your MCQ also, for your terminal exam also. So I planned in that way resonance. Okay, so by tomorrow I want to start the next topic, coupled circuit. Okay, the next half of unit 5, second half of unit 5. So we completed the first half of unit 5, resonance. The next one is coupled circuits, that we will discuss by tomorrow. So till now, any doubt? So if you have any doubt, you can stay, otherwise you can leave. So thank you, thanks for your attention.